Hello students, Mr. Mannix here and welcome to our lecture on work and energy. So, let's get started. What is work and energy? A lot of us are familiar with the terms, but we may not know what it actually is in physical science. So, for example, is this weightlifter doing work? How about these people? Often when we think of work, we think of maybe something that's hard, like packing something heavy around. Maybe we think of building a building, and that would be work. Maybe we think of going to a business meeting or some other type of office work. But in physics, we have a very specific definition of work. In physics, we say that you do work when you apply a force to an object and it moves in the same direction you applied your force, and we can calculate it with this equation. Work equals force times distance. And that would be where work is measured in joules, force is measured in newtons, and distance is measured in meters. Okay, so over here, a pushing force does no work if the wall does not move. So you can apply all the force you want. If you don't move an object, according to physics, you actually don't do any work. However, now if you were to move this wall, a measurable difference, now you are doing work. Let's look at some more specific examples here. Okay, when do you do work and when don't you? Okay, so let's say I apply a force. Maybe there's a couch sitting here. And I'm helping to move this couch, and so I apply a force to this side of the couch of 10 newtons, and I push that couch a distance of 10 meters across the floor. Then I do work, and it would equal force times distance equals 10 times 10 would equal work of 100 joules. What about if I had the car, and let's say this is a car here. It's going to be really roughly drawn, and let's say it's driving straight forward. And as it's driving forward, and let's say it drives a distance of 20 meters, well, 26 is what that looks like, so we'll call it 26 meters. But I walk up to the side of the car, and I push with a force of 10 newtons. And I walk alongside the car this whole time that it's rolling these 26 meters, and I push sideways with a force of 10 meters. But let's say this car doesn't move to the left. Okay, it does not move to the left. Did I do any work? The answer is no, because even though I applied a force, the object didn't move in the same direction as my force. One more example, and they like to give this example in the book. But let's say there's a person carrying a box. Okay, so this person carries a box all the way across the room. Okay, and it could be a heavy box, and they say, well, do you do any work on the box? And a lot of times your textbook will say, well, no, you don't. Why do they say that? Well, they say because your hands are mainly applying a force upwards on this box, and the box is moving to the left. Therefore, you wouldn't actually do any work on it. Now, that's not entirely true. You do some work on it. The work you do is your legs pushing against the floor in this direction, and maybe, I guess, the friction between your hand and the box that's pushing this way. Whatever force you exert to the box to move in that direction, to the left, that would equal work equals force times distance, and you would be doing work on the box. But the force that you apply upwards on the box does not count for the work you're doing. All right, when we do work to something, we transfer energy to it. We can look at some examples here. For example, the force acting on this roller coaster here would be gravity. And gravity does work to the roller coaster and adds energy to it. In other words, as it falls, gravity applies a force over a distance, and the roller coaster gains kinetic energy. This kid that's pulling back the bow, he applies work to the bowstring. He applies a force and moves it over a distance. And so he is doing work to the bow, and he's adding energy to it in the form of stored elastic potential energy. This weightlifter working on this bar, he applies a force to the bar. He moves at a distance from the floor to above his head, and he does work to the bar, and the bar gains energy in the form of gravitational potential energy. So work can also be described this way. Work is equal to a change in energy. And so one thing you'll notice is that work and energy are both measured in joules. So both work and energy are measured in joules, and work is equal to a change in energy. So if I apply work to a barbell, and let's say I lift this barbell 10 meters, and the barbell goes from having a potential energy, a gravitational potential energy of 0 at the bottom, to let's say it has 1,000 joules of energy at the top. Well, I must have done 1,000 joules of work then. If there is a ball sitting on a cliff and it has 1,000 joules of potential energy, gravitational potential energy at the top, and it falls to the bottom, it would have 1,000 joules of kinetic energy just before it hits the bottom, and gravity would have done 1,000 joules worth of work on that object. So work, the amount of work done, is equal to the amount of change in an object's energy. Okay, so finally, solving work problems. We're going to go through 4 different types of problems. Okay, the first type of problem is when they give us the force and the distance, and they ask us to calculate work. So this would be a question like, you apply a force of 20 newtons to a couch over a distance of 50 meters. So that's a long ways to push a couch, but let's say you push a couch with a force of 20 newtons for a distance of 50 meters. Then work equals force times distance. Work equals 20 newtons times 50 meters. Work would equal 1,000 joules. Remember to make sure that our units are newtons for the force, meters for the distance. Okay, what about when we're asked to find a distance? So this problem would be written up something like this. Somebody does, let's say, a boy does 150 joules of work when he pushes, well, let's see, when he lifts a box with a force of 100 newtons. Okay, how far did he move the box? Well, work equals force times distance. I know I did 150 joules of work, and that's going to equal my force of 100 newtons times my distance. I'll divide by 100 on both sides. That cancels. 150 divided by 100 is 1.5 meters would equal the distance. Okay, third type of problem. You can probably guess it. Now it's going to ask us to solve a problem where it's asking us for the force we apply. Let me fix this really quick. Okay, when asked to find force. Okay, so this would be something like a mover applies a force to a grand piano and moves it a distance of 10 meters. In the process, the mover does, let's say, 1,000 joules of work. So now they're asking, how much force does he apply? Same equation. Work equals force times distance. 1,000 joules equals the force times a distance of 10. Divide both sides by 10. Force would equal 100 newtons. Alright, finally, last type of calculation to be aware of. When gravity is the force that does the work, sometimes there's a special condition we have to watch out for. What if they say that you lift a 10 kilogram weight a distance of 1 meter? How much work do you do? Well, we got to be careful because this is a mass, not a force in newtons, but they do give us a distance. However, when gravity is involved, we can always calculate the actual force, because we know that force equals mass times acceleration. We know that this is the acceleration due to gravity, so we say force equals mass of 10 times the acceleration due to gravity of 9.8. Force equals 9.8 meters per second squared. And now I can plug that into the work equation. Work equals force times distance. Work equals a force of, oops, I did this wrong back here. 10 times 9.8 is 98 newtons. So work is equal to 98 times a distance of 1. Work would equal 98 joules. So again, if they give you a mass, such as 10 kilograms, and they ask you about how much work something does, someone or something does on an object, we can find the amount of force by using F equals ma, mass times acceleration, where acceleration equals the acceleration due to gravity, which is 9.8 meters per second squared. Alright, that's it. That's our lecture on work and energy.